All right, what we want to look at here is let's look at an example. We're going to both find what a function would be integrated over given some constraints, and then we'll find the volume by setting our function to be 1. So this is example 1 in the textbook, and example 2, I think. Yeah. No, example 1 and example 3 in the textbook. No, the textbook doesn't do the volume at all, but we'll work out the volume, I think. Example 1 plus its volume. And so what we want to do is we're going to let S be the sphere of radius 4. Or radius 5, sorry, radius 5. Centered on the origin. And D be the solid region. That is under the sphere. And above the plane Z equals 3. And we'll probably have to do a couple of different graphs to make this work for ourselves here, but let's start drawing this. So since we have a sphere, I think my x and y needs to be a little more depth. Let's see. Let me get that exactly lining up here. There's my x-axis. Let's get my y-axis here. And then in my z-axis. All right, so there's our places in space. So we're looking at a sphere that has a radius of 5. So I'm going to go up 5. 1, 2, 3, 4, 5. These are diagonals, so 1, 2, and they're squash diagonals. So let's see. 1, 2, 3, 4, 5. I'll use doubles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll make this Z equals 5 for the top of my sphere. And if I'm looking at the projection downward at the top of the sphere, this is going to go 1, 2, 3, 4, 5. It's going to curve down to negative 5 in x. And positive 5 in x. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So, yeah, this looks a little tall here. I'm trying to think about how the vanishing point perspective. I guess that looks closer to 5. All right, I'll work on. Right, I don't have perfect isometric graph paper here because I don't have a vertical axis, but yeah, we'll make this Z equals 5 here. And so the top of my sphere is coming down like this, circularly. circles here. Right, and so there's the top of my sphere. So our plane is going to cut through at z equals 3. So this plane cuts through our sphere at z equals 3. So it cuts the sphere here, kind of creating a dome. And so we want to see both the shadow of our dome, our shadow region of our dome. So this extends down to here and extends down to here. And so the shadow region comes down around the origin, and we need to know how far, what the radius of the circle would be. And this is where I'm going to draw a little off to the side here, because what we have looking at a cross section of the z plane and any of the other axes is we have the radius to the sphere is a radius of 5. So this goes up to 5. And then in the plane at 3, cuts off like this. But at one point, as this comes down, there's a place where they intersect. All right? So we're coming down, and so this has a height of 3 here. And we need to find this intersection point. Well, this is the radius here, and this is also the radius here. So that hypotenuse has a length of 5. And that triangle is a 3, 4, 5 triangle. But even if we didn't have a nice 3, 4, 5 triangle, the Pythagorean theorem would tell us what this radius is. And so we have a 4 here. So that means this is a radius of 4. The shadow that we see is going to be a circle of radius 4. And so we have the shadow circle of radius 4. That's our region R on the bottom here. I'm starting to get a cylinder out of my shapes here, but we have this filled in region R. And so my job now is to find some points from the region. So we'll take some point here and we'll project it through our solid region. And so this is M. And when M punctures through the lower portion, well, Z is going to equal 3. And then when Z punctures through the upper portion, well, that's when it's piercing through the sphere. And our equation for a sphere centered at the origin right? X squared plus y squared plus z squared equals 25. But we're going to solve this for z. So z is going to equal 25 minus x squared minus y squared square rooted. And so that's going to be the upper limit here. So we have the upper limit of our piercing through our solid region D. And then we want to take something parallel to the y-axis. We want to figure out when it pierces and leaves the circle that we're moving through. So this is our line L. And when L pierces the circle here, all right, well, what is the equation for the circle? Well, this is a circle with a radius of 4. So x squared plus y squared equals 16. Y squared equals 16 minus x squared. So y is both the plus and minus 16 minus x squared square root. And when it comes in through this, it's puncturing the lower version of that, so it's taking the negative. And when it comes out here, it's hitting the positive. And so now we have enough to really get our integral together. So if we take our z value, our z is going to enter at 3 and leave at 25 minus x squared minus y squared. Our y is going to enter at negative 16 minus x squared, all under the square root, and leave at the positive version of that. And then in our x values are going to go from negative 4 to positive 4, because that's the radial sides of this. And so we now have an integral over that solid region D, formed by this sphere cut off at the plane of z equals 3.